anda aqui, vai cair, ele pega o Santana lá e cai, fica do lado da sua pública.
Acho melhor então pegar o Santana. Mas demora muito? Ah, entendi.
Mais ou menos isso.
Então é mais fácil de Uber.
Mas vamos ter um vai.
Tá.
Vamos mandar aqui pro Fábio avisar a gente quando tem um intervalo,
Tá.
que a depender, né? A gente pode chegar no intervalo ou antes do intervalo.
E se ele quiser fazer alguma saúde? Se ele quiser fazer alguma coisa, acho que só vai ser coisa rápida, porque também tá cansado, doente. Mas eu tô achando que ele não vai não. Importante combinar, né? O convite foi feito. Tem
E os passos estão muito diferentes.
O Iago queria isso daqui, sabia? Antes de ir para São Carlos lá comigo, nossa, faz uma década isso aí já. Aí ele prestou aqui para astronomia. Aí parece que caiu na segunda opção dele, que era física. Aí caiu lá em São Carlos, alguma coisa assim. Foi uma coisa meio de louco, assim. Aí ele abraçou e foi, né?
Bem caro pra caralho.
Ah, é caro.
Muito caro, bem, vai de ônibus mesmo.
Caro.
Uns 2 pau.
Aumentou.
Daqui a pouco eu penso, eu tento ver de novo.
Esses negócios também varia, né? Devia ter um preço fixo.
Nossa, muito caro, bem. Pior que tá cheio de Uber aqui na região.
Ah, pior que tá mesmo. E o cara veio falando, nossa, o cara bem legal.
Você fica assim? Então,
Não era bolsonarista,
pelo menos, né? Tem uns que gostam de puxar assunto. Não é sempre que eu tô a fim de conversar.
Ele ficou falando do filho dele, porque meu filho tá fazendo Unifest, tá fazendo relações internacionais. Aí começou a puxar, ele perguntou se eu estudava, daí eu expliquei que eu estudou, né? Ai, que bacana, não sei o quê. Daí, parabéns pelo curso.
Ele não tá querendo você, bem.
Não é nada. Ele tem namorado, você acredita?
Não acredito.
Tá demorando, pessoal. Só tem esse auditório, será?
Será?
Porque eu falei pra ela o nome do auditório, ela é aquilo lá.
Você falou o nome? Eu falei, não, por isso ela tá no auditório aqui. Eu sei que eu vim segue a mulher toda a vida e isso vai dar nele.
E ela falou, você veio pro seminário? Eu falei,
Vamos ver.
O senhor chegou já falou, comendo?
Tá pegando uma marmita lá.
Você tá brincando? Quando eu encontrei com ele, quer dizer, ele me viu, eu tava lá dentro e tava lá fora. Aí eu vi os equipamentos, assim que eu tenho os equipamentos, né? Toda hora tá passando lá, ó. E aí tava os equipamentos, colocando o carro, uma coisa assim. Sei lá o que ia fazer. Aí eu entrei, até com a mãe, mas
Aí eles falam, vocês vieram mesmo, eu já tenho outra jeito já.
né? Você viu o Joe falando que terminou de escrever ontem? Coitado! Tá mó nervoso, acho, né? Né? Última hora, eu pensei que era só a gente.
Não, não é isso. Vivendo a vida aí, né?
Pindaí, né? Você absteve assim?
Não escrevi.
Não escreveu?
Perdi prazo, não sei o que aconteceu. Mas eu gostaria de dizer assim.
Não, o meu drama? Boa tarde.
Funciona isso aqui?
Funciona.
Funciona?
Aham.
Acho que é melhor, né?
É?
Ele colocar.
Vai ter que usar porque tá sendo gravado.
Ah, tá sendo gravado?
É. Aí tudo que for falado aí tem que passar ou por esse microfone ou por aquele de mão que tá lá.
Tá. Uhum. You are being recorded. So, como é que liga isso?
Tá ligado.
Tá ligado já?
There's nice.
passador de slides.
Oi. Ah. Oh. It's going to work. Yes. Good. So this. Yeah. All right. Oh.
Não precisa do abraçador. Qual que é o... tá.
Excellent. Nice. Right. So. So. Nice. Nice.
This is being recorded already.
Yeah.
And when someone asks, do make a question for you, and it's not through the microphone, through this hand microphone,
Yeah.
and try to please resume or repeat the question on your mic,
Yeah.
so it gets recorded.
Yeah, will do. And
Você já quer começar ou já fecha?
Era mais uns 5 minutos, né?
Tá bom, se vai ser.
let's just stick that there. Oh.
falar que aqui não é um lugar de fazer pesquisa, que tem hospitalidade, não? De falar, não? De falar na reitoria, não? Do campo de falar, prefeitura do campo de falar, isto não é para os funcionários, não? Claro, no é lugar deteriorado para os turistas. Não fazemos pesquisa, não? Assim, não faz nada, não?
Are you okay with giving me some sort of hand signal in case I'm speaking?
Aí, ó, tá aqui, ó, já podemos conversar com ele. Oi? Você mesmo.
Pessoal, boa tarde. A professora Maria de Fátima está com um parente, um membro da família hospitalizado, ela não pode estar aqui, então ela me pediu para acompanhar, né, introduzir o Joe, seminário dele. Joe is working with us in a project, so he is from University of Surrey. And he's talking about metrology to exploit local sensors networks for applications in air quality and energy management. He's talking about his trajectory. He is a PhD student in England. Yes. Okay. Thank you.
Okay. So, good afternoon. My name is Joe Hayward, and for the past 9 months, I've been doing a PhD at the University of Surrey in collaboration with the National Physical Laboratory in the United Kingdom. I'm currently at the University of Sao Paulo for a collaborative project with IAG to develop low-cost air quality sensors for deployment around Sao Paulo. As a bit of a background, before starting my PhD, I did my undergraduate degree at the University of Southampton studying chemistry, where I focused on atmospheric chemistry or environmental chemistry wherever I could. Now I've moved on to the University of Surrey in the Environmental Engineering Department, looking at the metrology to exploit low-cost sensor networks for applications in air quality and energy management. Now, air pollution is becoming a global health crisis. World Environment Day, which has just passed, it was on June the 5th, focused on air pollution. London, in the United Kingdom, has breached the legal limit for nitrogen dioxide pollution every year since the limit began. Now, this normally occurs within the first few days. However, in 2018, it occurred within the first month. So there is a small improvement, but it's still a very big problem. Now, the measurement of air quality is very expensive. The equipment costs a lot, it's very big, it needs a dedicated site, and it takes a long time to maintain if you want to keep the accuracy of the measurement. This makes dense measurement networks very, very difficult. However, low-cost air quality sensors are trying to get around these price, size, and maintenance constraints. Now, because of their low cost, they are more prone to errors and noise from electromagnetic interference, etc. However, despite this, they have proved very useful in the field, making them a popular topic of research in the field of metrology, the science of measurement. Now, there are two main networks we're going to be talking about in London. The first is the London Air Quality Network. You can see it on the map there in cyan. This is a high-cost reference network, very similar to CETESB. It is one of the densest reference networks in the world, and there are over 70 sites currently dispersed all across London. Now, they measure a wide range of pollutants, nitric oxides, ozone, particulate matter, etc. And they are placed in a very scientific fashion in order to cover the wide range of regions in London and accurately map the air quality throughout all the different areas. Now, another network which has been recently set up is the Breathe London network. You can see the pods there in red. This is a low-cost monitoring network utilising AQ mesh sensors provided by Air Monitors. Now, as opposed to the very scientific nature of the London Air Quality Network, the Breathe London network has opted for a more public-facing way of approaching it. So many of these sensors are deployed near schools and other areas of public interest. There are around 100 sensors currently active around London, and they measure most of the same pollutants as the London Air Quality Network, though the Breathe London network also measures carbon dioxide. Now, the Breathe London network was set up to complement and not compete with the LAQN. It does have a faster frequency of measurement, but the LAQN is a far more accurate network. Now, the LAQN is very useful for scientific purposes. However, it can occasionally suffer from drifts in the measurement, as well as issues of the timings of the instrument falling out of sync. So every 6 months, a ratification or checking process is done on the London Air Quality Network to check the instruments, maintain them, calibrate them, and correct the data if necessary. The Breathe London network is designed so it shouldn't have to go through any of this process, but it's an experimental network at the moment, so we're going to have to see how things go later on. Now, here is an expanded map of London. So you can see the LAQN sites there, the Breathe London sites there. This blue area in the centre is the ultra-low emission zone, which was very recently set up in London. And the purpose of this zone is to prohibit vehicles that don't meet a certain air quality standard from entering the centre of London without paying a charge of between £20 or £30. This zone was only set up recently, so it's very difficult to tell how much of an effect it's had yet, but in the future we're looking forward to looking back at the data and seeing what kind of an impact it's had. Now, it was brought to my attention that several people here believe that London's air quality is fairly good. Unfortunately, I'm going to have to disprove that. So this is Marylebone Road in London. This is one of the most polluted sites I have worked with. And you can see here is one of the reference monitoring sites. Marylebone Road is a very well-off area and considered the reference site an eyesore. So they built this wooden structure around it to make it blend in better with the environment. Now, particulate matter of a size less than 2.5. There are two values listed here. This is a rough calculation of the UK annual average that I did across all the sites in the UK. This isn't the official average, it's just a rough guideline. We also have EU legal limits for the pollutants. So the legal limit for PM2.5, 25 micrograms per metre cubed for an annual average. Now we can see particulate matter is quite a big problem in London. We're getting spikes of over 100 micrograms per metre cubed, which is a big concern. You can also see two big peaks here, which are extended episodes of particulate matter pollution. Now, these are most likely not localized to the UK. When the wind blows in from the east, we pick up quite a lot of pollution from Europe, so it passes over quite a lot of agricultural areas in Belgium, picking up a lot of particulate matter pollution and depositing it in the UK. So these trends weren't just seen at Marylebone Road, they were seen all across the United Kingdom at every reference site. Now, particulate matter of a size less than 10 microns, it follows a very similar trend as you'd expect. There are two legal limits for this one, 40 micrograms per metre cubed annual average and a 50 micrograms per metre cubed daily average. And in brackets, you can see it says 35 times. This means all the sites of the UK can breach this limit a total of 35 times before they've effectively broken the law. Now, as you can see here, a lot of spikes in PM10 again, particulate matter is quite a big problem. However, when you compare it to nitric oxide pollution, you can see the scale of pollution in London. So there is no current EU legal limit for nitric oxide. When these limits were being set up, they decided that as nitrogen dioxide levels and nitric oxide levels correlate very well, and nitrogen dioxide is easier to measure, that they would just set the limit for nitrogen dioxide. However, here you can see levels of up to 500 micrograms per metre cubed. Nitric oxides are a big problem in the UK, mirrored with nitrogen dioxide. Now you can see here the EU limit is 40 micrograms per metre cubed annually and 200 micrograms per metre cubed hourly average, and the sites can breach this a max of 18 times. Now we can see Marylebone Road itself has breached this at least once in 2018. It has most likely done so many more times earlier on. And it's not just this site. There are plenty of polluted sites in London that will have also breached this limit, as well as some in South Wales. Now, ozone, on the other hand, actually fairly low levels. And this may seem surprising, but ozone reacts with nitric oxide to form nitrogen dioxide and oxygen. So in any environment where you have an excess of nitric oxide, you'd expect to see fairly low levels of ozone. Now, let's contrast this with Ladybower. This is a very isolated reference site in the rural north of England. It lies to the west of Sheffield and to the east of Manchester and is close to a reservoir. This is a very isolated area and you'd expect very little pollution. And you can see that in the nitric oxide levels there. So very low, almost zero levels of nitric oxide most of the time. There's very little to worry about with that. However, the ozone levels there are much higher than Marylebone Road in the centre of London. A big problem we have in the UK is with the transport of pollutants. So just because a pollutant was generated in the city is its source, it can be moved via wind and other factors and end up in very rural areas like this. And this site is consistently quite bad for ozone, as you can see, with very little nitric oxide to take it up. Now, why are nitric oxides and particulate matter such a pollutant in the UK? Well, in 1998, diesel cars accounted for 12% of all cars in the United Kingdom. However, when people were starting to get quite worried about global warming, politicians looked at diesel cars and petrol cars and realised that diesel cars emitted less carbon dioxide and were more fuel efficient. Looking at these single statistics, they then heavily promoted the use of diesel cars through tax incentives and other measures. You can then see the rise in popularity of diesel cars from 2002 to 2017. The proportion of diesel cars on the road peaked at 40% in 2017 and dropped to 39% in 2018. Now, this is most likely partially due to the Dieselgate scandal, which was all across Europe a few years ago. This was where car manufacturers, particularly of diesel cars, were cheating emissions tests in order to make their cars seem far cleaner than they actually were. The tests have now been changed, so this can't happen again. But this was a big scandal all throughout the EU. The UK government is also now trying to convince people not to use diesel cars anymore, and I believe they are banning the sale of them within the next 20 to 30 years. Now, there are several sources of nitric oxides. Thermal nitric oxide, which is chiefly produced above 1,300 degrees Celsius and barely produced below 760 degrees Celsius. So during the combustion process, elemental nitrogen is oxidized, forming nitric oxide. There are also fuel nitric oxides, where fossil fuels such as coal and oil contain a small amount of ionized nitrogen, which is then also oxidized during the combustion process, increasing the amount of nitric oxides. Now, there is a third element, prompt nitric oxides. This is where the elemental nitrogen combines with hydrocarbons in fuel-rich conditions and then oxidized alongside the fuel. Now, the United States Environmental Protection Agency debates how much of an impact prompt nitric oxides have, as it very much depends on the engine. So this is normally discounted when talking about this. So diesel engines are hotter than petrol engines, so they produce more nitric oxides. When the government was promoting diesel engines, they inadvertently caused a large rise in nitric oxide and particulate matter pollution throughout the United Kingdom. And you can see here a list of equations that nitric oxides undergo. Some of these compounds are very stable, allowing them to be transported large distances, which is how you end up getting ozone and nitric oxides in rural areas where you wouldn't normally expect them. Now, this is a map generated by King's College London. It is a model of the annual mean nitrogen dioxide concentration in London in 2013. This isn't peak levels, this isn't an hourly average at rush hour, this is the annual mean throughout the entire of London. And yellow corresponds to about 50 micrograms per meter cubed. Red corresponds to 80 and above, so very dangerous levels, and this is an annual mean. So you can see here, large amounts of central London would have breached the annual mean limit. The North Circular, also very polluted. We have Heathrow Airport over here, also suffering a lot of pollution. Kingston upon Thames down here. So nitrogen dioxide, massive problem throughout London. But how do we go about measuring that in a low-cost census system? The most common component to be used is an electrochemical or amperometric sensor. Now, these are used in most low-cost ambient air quality monitoring devices. These were originally designed for use in safety monitoring, so ozone while you're welding, etc., and were designed to measure micromole per mole or ppm levels of pollutants. However, when air quality was becoming a hot topic issue, they were repurposed for air quality purposes and designed to look at nanomole per mole or ppb levels. Now, this massive increase in sensitivity led to a massive decrease in the signal-to-noise ratio. So it can often be very difficult to get a measurement from these sensors and sort of remove it from the noise. This increase in sensitivity also means the signal is much more susceptible to many different forms of drift that we'll go into in a minute. The way this component works, your target gas would diffuse in, end up in the gas chamber, and come into contact with the working electrode, where it would undergo a redox reaction, either reducing or being reduced or being oxidized. This would generate a flow of electrons, which would generate a current, which would then be measured by your microcontroller, your data logger, or your computer to get a reading of the target gas concentration in the environment. Most electrochemical processes have three electrodes, the working electrode, the reference electrode, and the counter electrode. Some air quality electrochemical sensors also contain a fourth auxiliary electrode, and we'll go into the purpose of that in a second. Now, electrochemical sensors suffer from several different kinds of drift. The first is a temporary drift called measurement drift. This is generally caused by a change in temperature or humidity, increasing or decreasing the baseline. Cross-sensitivity with other gases can also be an issue. One example of this is nitrogen dioxide and ozone. So the way electrochemical sensors generally select gases to measure is by matching their redox potentials. The problem is ozone and nitrogen dioxide have very similar redox potentials, so are 100% cross-sensitive with each other. We'll go into the solutions for this in a minute. Noise is also a big problem. This can be introduced from electromagnetical interference, power supply issues, all sorts of things generating random errors in your measurement. Now, baseline drift is a permanent change in the baseline, and this is generally caused by a poisoning or degradation of the sensor element. Generally, when it starts changing the baseline, it will always continue in that direction. But this can cause permanent changes in the measurement and does need to be regularly checked and calibrated against. Now, how do you go about correcting for this drift? There are several mechanical methods you can use. For example, auxiliary electrodes. So these are secondary electrodes which are in a similar environment to the working electrode but are not exposed to the target gas. So their signal should only change with changes in temperature, humidity, etc., but not with a change in concentration of the gas you're trying to measure. Theoretically, you can then subtract the auxiliary electrode signal from the working electrode signal to get a more accurate measurement. Now, this doesn't always work. The auxiliary electrode is generally kept in a different environment to the working electrode, so it doesn't always follow the environmental changes as the working electrode would. Now, for cross-sensitivity, you can use filters to remove the cross-sensitive gases. As I mentioned before, nitrogen dioxide and ozone are 100% cross-sensitive. Their signals cannot be conventionally separated. A manganese dioxide filter removes ozone from the nitrogen dioxide sensor, but does leave it sensitive to nitric oxide. A PTFE, or manganese dioxide filter, removes cross-sensitivity with both. Now, there are some limitations to filtration. Not every gas is easy or cheap to filter out. For example, nitrogen dioxide. Now, the way you can get a pure ozone signal is by doing the following. If you assume the oxide signal to be proportional to the sum of ozone and nitrogen dioxide concentration, you can then take the ozone signal to be the oxide signal minus the filtered nitrogen dioxide signal. However, this process does require both an oxide and a nitrogen dioxide sensor, which may be overkill if you're just looking for ozone. Now, a way of detecting the permanent baseline drift is by generating a zero gas. You can either do this with a zero gas generator, as pictured here, or by building a filtration setup that you can attach to your sensor and leave to run. So by generating a zero gas or removing your target gas, you will get just the baseline of the signal from your sensor. By measuring this zero value at regular periods, you can see how it's drifted over time and then correct for that via software. Now, there are several software methods for removing drift as well. The simplest way of getting a measurement out of your sensor is by using linear calibration. So by taking your sensor's output on the x-axis and your target gas concentration on the y-axis, which you can obtain through either a collocation study or the use of reference gases, you can then get a very simple slope and offset to get a rough measurement for your sensor. The problem is, if this doesn't account for temperature or humidity, etc., you're going to get a very poor measurement. By using multivariate linear calibration, you use not just the sensor output, but also temperature, humidity, cross-sensitive gases, anything else that is scientifically known to directly affect your target gas's value. By then accounting for all of these in the calibration process, you can much more effectively counteract measurement drift and get a better measurement as a result. Many machine learning techniques can be used as well. There are some limitations to this process. Some calibration methods only work if the conditions the sensors were exposed to and trained on are also present in your measurement conditions. So for example, if you've trained your sensor in a range of conditions between 15 and 30 degrees Celsius, not every algorithm will respond well if you put that sensor outside of those conditions. So if you deployed it in an area that was at 10 degrees Celsius, you'd get a very poor measurement out of some algorithms if you got a measurement at all. Now, this isn't a limitation for multivariate linear calibration, as it looks at trends in the data rather than using a set of rules. So it can work outside of its trained range. Now, as part of the Breathe London network, we have been doing a collocation study at the National Physical Laboratory. So this is utilising several AQ mesh sensors, as well as 2 Google Street View cars, which are fitted with very high frequency, high cost measurement equipment for the same pollutants that the Breathe London network is measuring. We also have an automatic urban rural network reference site at MPL measuring PM2.5. This is also similar to the CETESB network. An automated comparison program was then developed and run by me to determine the correlation between all of the sensors. So we can see here, many of the pods perform very well. This is a comparison of PM2.5 between one of the AQ mesh pods and the reference site. We have generally a very good correlation there. We have the comparison of nitric oxide between 2 of the pods. This is a surprisingly good agreement. We are very happy with how well both of the sensors perform there. We also here have a comparison of ozone between one of these Street View cars and one of the AQ mesh pods. You can see here at the end there is a slight non-linear trend. This could be due either to the pod or the Google car. Further tests will have to be run to determine. However, not all pods are made equal. One of the Breathe London pods we received at the start of the network had a damaged particulate matter sensor. So you can see here, whereas one of the cars was reading about 0 for the levels of PM1, the pod was reading anything from 5 to 100 micrograms per meter cubed. Luckily, this pod was taken away and this problem has now been repaired. Now here we have 2 more of the Breathe London pods, and these are completely uncalibrated pods. So these pods aren't meant to be used for nitric oxide and nitrogen dioxide. So this is just an example of what happens if you have a very poor or no calibration of your low-cost sensors. You get useless measurements. These mean effectively nothing. Now, as part of my project at the University of Surrey, we've been designing our own low-cost sensor to be deployed around the campus. The reason we want to use our own one instead of using one by a manufacturer is manufacturers tend to be very secretive about the methods they use for building their sensors, how they calibrate them, how they look at drift, etc. By building our own sensor, we can get very low-level access to the data and design many more experiments around these sensors. When designing them, we needed to balance cost, usability, and data quality. Cost because it's a low-cost sensor, usability because we want to use it in a range of projects, and the data quality because if the data is of a poor quality, it's not going to make my PhD look very good. So we can see here at the top left, we have a particulate matter sensor. This is a standard optical particle counter, though it's very good quality from AlphaSense. We also have 3 electrochemical sensors looking at ozone, nitric oxide, and nitrogen dioxide. The ozone and the nitrogen dioxide together are very important. We also have 2 fans to maintain airflow throughout the system. A big issue with electrochemical sensors is if there isn't a constant airflow of them, they tend to stagnate and give very poor measurements, even if exposed to the open air. So an airflow is always needed. Now, future work for the project. For the Breathe London project, the preliminary data is going to go live soon on the Breathe London website. This is currently planned for late June, and you can see the link there. An algorithm is currently being developed by myself to calculate the uncertainty on the network with the help of data from the London Air Quality Network mentioned earlier. Once this data is live, it can be used to advise people in London about the air quality in their area. Future work with the University of Sao Paulo. Similar sensors to the one I've designed will be calibrated and deployed around Sao Paulo. I will give assistance for the calibration, data analysis, etc., to get a broader picture of the air pollution around the city. This data may then also be used to build an air pollution model of Sao Paulo, similar to the LAQN model in London. And future work with the University of Surrey, we are planning on building 8 of these sensor systems for deployment around the university. We are going to network them and periodically use reference equipment to check them for drift. We are going to use multiple calibration techniques, including machine learning techniques and linear regression, to determine the best calibration technique for environments like the University of Surrey. And we are also going to determine the best way to allow university staff and students to access data. Because a big focus of this project is making sure the public is informed about the air quality in their area. Thank you for coming to my talk. Are there any questions? Cool.
Hi, Joe. I'm Enrique from the University, from the Institute of Physics across the road. You mentioned the importance at the beginning about the drifts in the sensors, but you didn't actually show data on that. I wonder if you could make comments on how often you need to do those calibrations and how long do they stay?
So yeah, it varies in the literature. So generally you need to perform recalibrations within a few weeks to a few months of deploying the sensor, most likely due to a few weeks. The AQ mesh sensors appear to have some sort of correction algorithm inbuilt, so we haven't noticed as much drift with them as we would with just electrochemical sensors on a circuit. But yeah, generally in the literature, it's pretty much agreed within a few weeks you'd need to recalibrate to account for this baseline drift. It's very quick.
So you need to take them back to the lab to do the calibration?
We're going to try and avoid that by looking at certain machine learning techniques, a portable calibration kit, and some sort of time-based calibration method as well, just to try and see if we can catch this drift and have to take it back to the lab less often. Another option is to just deploy them at a reference site and co-locate them for a few days to account for the drift, but that's still a lot of effort moving the sensors to this site. That's the big sort of drawback with these low-cost sensors, is the fact you're going to have to move them back and forth every few weeks.
Alfredo from Institute of Physics. When you choose the detector for CO2, you have looked at the optical sensors also.
So yeah, our sensor kit doesn't currently have a CO2 sensor, but if we were going to put one in, we would use an optical one. We have used optical ones previously.
This one is best.
The optical ones, they're generally the cheapest and they generally work quite well. So yeah, optical sensors are the way to go for low-cost sensors generally, in my experience.
Hello, Leonardo from IAG, and how do you do the system of the source power limitation of your sensors? It's the limitation directly in the power network disponible side in the area, or it's
So the AQ mesh sensors in the Breathe London network are mostly powered off the power grid. So they're hooked up to the lampposts and things like that to draw their power.
Right.
Some are solar powered, which has actually worked quite well, which is surprising in the UK because we don't get a lot of sun. But the sensor kits we've got for Surrey are battery powered, but would need to be plugged into some sort of USB power supply to periodically charge the batteries. So there are a wide range of ways of going about it.
Great, thank you.
More questions?
Hi, I'm Thalita from WRI Brazil, and I have a question. If are you considering to make the connection with short-lived climate pollutants like PM2.5 or ozone or maybe consider this question if in your results.
Could you repeat the question? Sorry.
If are you considering discuss about short-lived climate pollutants like PM2.5 or ozone? Because we are starting to work with this kind of measurement of air quality to do the connection with climate change. And my question is if you are considering using this kind of connection in some way.
So the short-lived nature of them, so the way they tend to disperse or decompose quite quickly, depending on the pollutant?
I think I can talk to you later, maybe try to explain that.
Yeah.
Thank you.
Which department are you doing your PhD?
At the University of Surrey.
Yeah, but it's like in the Physics Institute, Metrology Department.
The
where
Department
are you
of Environmental Engineering.
Okay. My question was I see that in the instrument, let's call that, that you are developing, you use sensors that are available on the market.
Yeah.
I wonder if you have contacts maybe in the physics or engineering departments that could help develop new sensors, like cheap sensors, but homemade, that could help do these measurements.
Yeah, I think there are a few contacts. There are some specifically at the University of Surrey that are beginning to work on it. And there are also some at the National Physical Laboratory, which have done some work in air quality sensors in the past, sort of developing their own. But I think those are both too early on to be able to use in the kind of projects we're doing. A few years down the line, I'm very early into my PhD, so a few years down the line, hopefully we'll be able to use some of these sensors that are being developed, but for now, we're having to rely on market-based ones.
Yeah, hi, thank you for your nice presentation. I'm Marcia from here. My question is about drifting the sensors. How long can we use or how long can they survive after calibration that you say, no, I cannot use it anymore because it doesn't stay?
Worst case scenario is probably about 2 weeks.
2 weeks?
Yeah, your best case scenario is probably no more than 2 months.
2 weeks goes away?
Yeah,
Wow.
2 weeks, and then the baseline drift is significant enough. You might have
but then you recalibrate and reuse
Oh
it.
yeah.
No,
Okay,
I mean when you have to throw it away.
The alpha sense sensors, it's generally about 2 years.
Okay.
So they
good.
contain an electrolyte solution which evaporates over time. The lifetime of the sensor varies depending on the manufacturer, but the alpha sense ones we're using are 2 years.
Okay, good. Thank you.
Is there some kind of thing that you can do with the drifting analysis? Like, I don't know, maybe you took a sensor of reference in your institute, and you analyze the drift of the drifting of the sensors, and maybe, I don't know, with the machine learning processes, maybe you can use this to calibrate it in longer periods of time, or you think it's possible? You think it's, don't know, maybe?
So using multiple low-cost sensors to calibrate themselves?
No, not like that, because it's not work very well because the difference between the positions that you put it, but the drifting of the drifting, you know, like if I know how many the drift increase with the meteorological condition, I can make a comparison between the data before and after, estimate the drifting, and put a correction on the signal by this. So the individual electrochemical sensors aren't made equally, so the effects of temperature and humidity can affect two electrochemical sensors manufactured at the same time very differently. So that's why you need a multitude of these processes. Yeah, but it's occurs very differently in time by one sensor, or you are saying that it's different between the sensors?
Different between the sensors at the same time.
Yeah,
that's one of the problems with the calibration processes as well. You need to calibrate the kits individually. You can't calibrate one and then apply that to the rest.
Yeah, of course. Yeah. But you can't do algorithm to extend this calibration once one sensor by time and all.
You might be able to, yeah. I've got some papers I might be able to show you after this.
Oh, great.
Yeah.
Thank you.
Mais questões?
Hi, I'm Carlos from IAG. Did you have to think about the auto-calibration with gases in these sensors?
So using
to help auto-calibration, automatic calibration, to help this to correct.
So I think I touched briefly on it, but I don't think I mentioned it specifically. So you don't just need a zero gas generator with this.
Okay.
One of the papers I looked at used a filtration unit built into the sensor, which generated the zero gas automatically without any extra equipment or input from anyone. And they did this periodically at a certain time, over a 15-minute period, I think, and measured that drift. And it actually worked very well. Like, if you're willing to spend a bit more money, this is probably one of the best mechanical methods to counteract the baseline drift.
Yeah. Okay. Maybe you can help it to certificates to improve the confiability of these local sensors.
Yeah.
Maybe. Yeah.
Mais perguntas? Okay. Thank you, Joe.
Thank you.
Would you like to speak something?
Oh, no.